Welcome! Which is the more important greenhouse gas, carbon dioxide or water vapour? This video seeks to answer that question once and for all. When discussing the greenhouse effect, there's often an elephant in the room. You'll see many diagrams rather like these. It shows that carbon dioxide makes up 82% of the global warming, and that transportation and electricity make up the lion's share of the carbon dioxide contributed to cause that effect. However, there is something that is always forgotten to be discussed in these sorts of things, and that is water vapour. It's the elephant in the room. We can take a look at this quantitatively and see which is the gas that creates the most effect of global warming. Water vapour makes up 50% of the effect. Clouds, which you could argue is another form of water vapour, make up another 25%, and all the other greenhouse gases make up the remainder, but that is mostly carbon dioxide. So just from this simply, you would say that it's water vapour that is dominant overall, creating 75% of the effect. However, things aren't that simple. Let's discuss clouds for a while. Clouds indeed do warm the planet, but using a blanketing effect. They reflect infrared radiation from the surface of the Earth back down towards the Earth, warming it. But that neglects the other aspect of clouds, that they also reflect away sunlight, increasing the Earth's albedo, which is a cooling effect. And it's very hard to tell what the net effect of those two. All we know is that the net effect is very, very small. So we can basically ignore the effect of clouds. So that leaves the water vapour producing about 2/3 of the warming, and all the other greenhouse gases, primarily carbon dioxide, producing 1/3 of the warming. Let's contrast and compare carbon dioxide with water vapour. Water vapour is a stronger greenhouse gas, about 3 times that of carbon dioxide. There's more of it in the atmosphere. On average, about 2% of the atmosphere is made up of water vapour. Although that percentage is highly variable, varying from 0% to 4%, depending on where you are in the planet and at what altitude in the atmosphere you are. It also has a very short life, which is measured in hours in the atmosphere. Carbon dioxide, on the other hand, is very uniformly distributed. It has a longer life, tens to hundreds of years, some people argue millennia. It is a weaker greenhouse gas, and the concentration is about 0.04%. So for every 1 carbon dioxide molecule, there are 50 water vapour molecules in the atmosphere. How much of the carbon dioxide in the atmosphere is from human pollution? If you go back nearly 1 million years, you can see that the carbon dioxide levels have varied from about 180 parts per million to about 280 parts per million. It's only in the recent few decades that the concentration has increased to over 400 parts per million. If you look back over the last 2,000 years, for most of that time, the carbon dioxide level in the atmosphere was about 280 parts per million. But around about 1800, that started to rise. So what happened in 1800 to cause that? Well, we started the Industrial Revolution, and we started burning an awful lot of coal. In about 1900, we started burning oil, and now we're also burning natural gas. What are the origins of that carbon dioxide? You can see that our emissions of carbon dioxide have now risen to about 9 gigatons per year. Most of that is from the burning of fossil fuels, some is from deforestation, and something that I didn't know about before is that cement emits a lot of carbon dioxide when it is cured, and we're doing a lot of building these days with cement. So how much has the carbon dioxide increased? Well, we can do a quick little sum of that. 405 minus 280 over 280 equals 44%. So humans have increased carbon dioxide content in the atmosphere by about 44%. Let's take a look at what happens in our atmosphere for a little while. We live in the troposphere, the lowest level of the Earth's atmosphere. In that layer, the temperature falls as a function of altitude to from about 16 degrees centigrade at the surface to about minus 50 degrees centigrade at the top of the troposphere. Why does this happen? Well, I'm showing you this part of this plot, and you can see that the Earth's temperature varies quite significantly with altitude. The first part, the troposphere, is mainly controlled by greenhouse gases, which warm the planet, and convection, which helps cool the planet. As the density of the atmosphere and the pressure of the atmosphere drop with altitude, any convective cells that move up expand. As they expand, they cool, creating this cooling effect. That's called adiabatic cooling. Above the troposphere, the temperature remains relatively constant for a few tens of kilometers, and then it starts to rise again. That's mainly due to the ozone layer, which absorbs ultraviolet light from the sun, warming the atmosphere to about 0 degrees centigrade. Once you get above the troposphere, once you get above the stratosphere, the mesosphere, there's no ozone left, so there's no heating, so the adiabatic cooling continues until you get up above 90 kilometers, where X-rays and extreme ultraviolet light is absorbed from the sun, and that again heats the atmosphere to much higher temperatures. The simple fact is that humidity varies. The maximum humidity at the surface of the Earth is about 4%, or 100 times the concentration of carbon dioxide. But humidity varies with temperature. The lower the temperature, the lower the humidity. If you look at the saturation curve, that's the top one of these curves, at about 16 degrees centigrade, the humidity is 4%. However, it drops off very rapidly as you drop in temperature. It also varies with latitude. Near the equator, the humidity is about 3 times higher than at mid-latitudes and about 10 times higher than near the polar regions. And you can see in these plots that also the humidity drops with altitude quite rapidly. The average humidity at the surface is about 2%, or 50 times the concentration of carbon dioxide. With the drop in temperature and density of the atmosphere as a function of altitude, the influence of water vapor drops the higher you get in the atmosphere. Meanwhile, the concentration of carbon dioxide in the atmosphere is constant with altitude to about 80 kilometers. So at the surface, there's very much more water vapor than there is carbon dioxide. But if you go up just 7 kilometers, the ratio now is 5 to 1, 10 times smaller. At 9 kilometers, there's as much carbon dioxide as there is water vapor. At 14 kilometers, the ratio is reversed, with 20 times more carbon dioxide than water vapor. With the density and temperature dropping with altitude, the mean free path of an infrared photon increases with altitude. So this is the sort of random walk process that an IR photon will have to go through once it's emitted from the surface of the Earth. Initially it's bounced around a lot, and many times it will be reflected back into the Earth only to be re-emitted again. As it goes up in altitude, the distance it travels before it hits a greenhouse gas molecule increases and increases until eventually it gets to a layer where it can escape from the Earth's atmosphere. So down low, where no photons are actually escaping from the atmosphere, is a heating zone. And the more carbon dioxide and the more water vapor you have, the more steps that will be taken in that random walk, the longer the photon will spend in that time, the greater the chance it will be reflected back to the Earth, and the thicker that heating zone gets. Above that, where there are relatively few encounters and eventually the photons escape, is a layer which is a cooling zone. This is the layer that cools the atmosphere. This is responsible for our actual temperature. And that layer is mainly controlled by carbon dioxide, not water vapor. By the time you get there, there's very little water vapor left. The Earth emits infrared radiation in order to cool down, and because of the range of temperatures that the Earth emits, most of the cooling goes on between 10 and 24 microns in wavelength. This is in the infrared. So there's the outline of that emission profile, and this is the absorption spectrum of the Earth's atmosphere. And you can see right in the middle of that there's a band that is carbon dioxide. And at longer wavelengths, water vapor is very important. At shorter wavelengths, it's ozone. But there's a nice window here between 8 and 14 microns that is where Earth primarily cools. Now as the Earth warms up, this profile moves to the left, and you might think that that's very good from the point of view that as we warm up, more and more of that emission profile gets into that window so it can find a new equilibrium at a relatively reasonable temperature. But to cause a shift like this, which would be what looks as though is needed, would require Earth temperatures to increase by something like 40 degrees centigrade. And if that happens, you and I aren't here. Another problem is saturation. Some people claim that both water vapor and CO2 are saturated, and I've marked where they are here, and indeed that is the case at some wavelengths. So they claim that adding more carbon dioxide or water vapor will make no difference to Earth's temperature. That is untrue. Let's take a look at what actually happens. Here is 4 line profiles of the carbon dioxide absorption feature at different concentrations of carbon dioxide. So at low concentrations of carbon dioxide, i.e. high in the atmosphere, that line is not saturated. However, as you add more and more to the amount of carbon dioxide in the atmosphere, the wings of the line are expanding. So what effect does that have? Well, let's take a look. I've marked here the window boundary on the long wavelength side of that carbon dioxide feature. And what happens if you add more carbon dioxide? What will happen is that that shoulder of that feature will move to shorter wavelengths. So as you add more carbon dioxide and the temperature goes up, and this profile moves to the right, the window effectively starts closing more and more. So you're in fact, in some sense, being counterproductive here. So what happens if we keep adding more and more and more carbon dioxide? You'd get an Earth that looks rather like this, a desert planet. So which is the most important greenhouse gas? Although there is more water vapor at lower altitudes, carbon dioxide controls the Earth's cooling at higher altitudes. So the more carbon dioxide you add, the more heat is trapped, the more water vapor is added to the air, so there's more steps in the random walk to try to get those IR photons out of our atmosphere. And also the cooling zone moves higher, and so it takes longer to get rid of that heat. So overall, that's a heating effect. We often hear about what would happen if we doubled the level of carbon dioxide in the atmosphere. Well, what would happen? It would increase global temperatures between 2 and 4 degrees centigrade, it is estimated. But you've got to note here that land areas warm a lot more than the oceans do, and there's more oceans. So land areas will warm tremendously. And you can see here that some land areas are going to be warming by 16 degrees centigrade, which is a tremendous increase in global temperatures. The effect would last for centuries because it takes that long for the carbon dioxide to wash out of the atmosphere. Okay, what would happen if you doubled water vapor in the atmosphere? It would rain. And in a few hours the climate would just return to normal. So this is the difference between carbon dioxide and water vapor. Water vapor is, because its lifetime in the atmosphere is so short, it cannot have any major effect on the atmosphere. It merely acts as an amplifier to whatever happens with the other sources of forcing in the climate atmosphere. And you can see that here. Carbon dioxide is doing most of the forcing, and most of the feedbacks come from water vapor and clouds. So, which is the more important? Water vapor or carbon dioxide? Carbon dioxide is the general here. It orders around what the other greenhouse gases are going to do. Water vapor, though there are more of them, are the soldiers. They do a lot of the work, but they're not in charge. That's all for today. Thanks very much. Until next time, goodbye.